Thanks. Okay, so I'll be talking about matrix multiplication, and this is a tensor workshop, so I first have to give you a little bit of an introduction on how matrix multiplication relates to tensor, but it will be fast. Okay, so matrix multiplication, we're given two n by n matrices. You want to compute their product, which is also an n by n matrix. And let's say the entries of the matrices are over some field, let's say the complex numbers. And I want to compute I want to know how many arithmetic operations do I need to compute this product, where the operations I allow, let's say, are additions and multiplications over in the underlying field. And so this relates to tensors in the following way. So there's something called the matrix multiplication tensor, which we denote n by n by n whenever it's n by n matrix multiplication. And it basically encodes this trilinear form. The trilinear form tells us, if you look at the coefficient in front of zki, it tells us the product over j of x psi j times yjk, which is exactly what you want to compute when you're computing the matrix product of two matrices x and y, and z is the output. And then, so if you look at what this looks like in coordinates, this is a tensor, and this tensor lies in the complex numbers n cross n, tensor n cross n, and it has the following definition. It's 1 whenever in the I prime j, j prime k, and k prime I entry, whenever j equals j prime, k equals k prime, and I equals I prime. So it's very nice. It has very nice structure, which we're going to try to exploit. You can then also define the tensor for m by n by p matrix multiplication. So when we have rectangular matrices instead of square ones, and it's exactly the same, except that now you live in m by n by p, and p by n over here. Okay. All right, so now there's a natural relationship between the rank of this tensor and the runtime of algorithms within this model of computation. So if you look at, suppose I have k by k matrix multiplication, and I have a bound on the rank, which is r, then there is a simple algorithm which performs exactly r times k squared additions and at most r multiplications. And when you look at what the rank decomposition of the tensor tells us, it tells us, well, we're actually computing R products, which is exactly the number of multiplications of linear combinations of one matrix times linear combinations of the other. And the linear combination only takes k squared time to compute in our model of computation, and there's R of them. So this is why there's R k squared. But, you know, if say we have a bound for constant k, then when we look at what it looks like when n grows, then you can apply recursion, because matrix multiplication is naturally recursive, and you can split the n by n matrices into k by k blocks of n over k by n over k, and you get that you have an algorithm which computes, again, the number of products is the bound on the rank of the matrix product, but the number of additions is now only Rn squared. So the additions are completely for free when we talk about big O notation. So this tells us why we talk about the exponent of matrix multiplication as, you know, the rank is it's h, such that the rank of n by n matrix multiplication is order n to the h, and it's known that it's an infimum. So you can get smaller and smaller ones unless it's 2. Okay, so this is the definition that we'll be working with. We will try to bound the rank of n by n matrix multiplication as n grows, and this will give us what omega is, and omega is what we're trying to hopefully prove that it's 2. But then we'll have a linear time algorithm for matrix multiplication.
So for people I've seen this before, the point is log k of r is at least 2.
Yes.
That's
yeah, it's always at least 2. Also, when we talk about algorithms, you have to
I understand.
give the output. But yes, yeah, and there's you know, actually, yeah, here for this, this is true, so it's always subsumed. Yeah. Good point. All right, so now we'll only be talking about rank. From now on, we'll forget about algorithms, but you can keep in mind that there is a natural correspondence between these things. Okay, so what do we know about omega? We know it's at least 2, and we know now that it's less than 2.373, which was a sequence of works, and the current best is you have 2 more decimal points here, which I'll give later. And Francois will give a talk later in this workshop about this. And the point of the rest of the talk is to give you at least some intuition about how we approach in getting these upper bounds. So what approach do we take and what hurdles we have to overcome. So in order to get into this, I have to mention that there's something called the border rank, which is like rank under limit. So this is a formal definition. You don't actually have to stare at it too long. You just, if you divide this red thing by epsilon to dh, this means that there is a sequence of tensors whose rank is always r. Let's say epsilon is some constant, and as epsilon goes to 0, this sequence of tensors goes to t. So we have a sequence of tensors whose rank is r and goes to t, and the border rank of t is then said to be at most r. And why do we care about this? Well, it turns out that the border rank can be much less than the rank of a tensor. And moreover, Bini showed that with respect to matrix multiplication, border rank is just as good as rank. So if we,
less border rank could be?
well, we don't know, but it can be half of it, right? The border rank could be half of the rank, yeah. But that's much less for our purposes. I mean, constants actually really matter. So, right. Okay. So the border rank can be smaller than the rank, and it's just as good as the rank with respect to obtaining bounds on omega, as Bini showed. And moreover, Schoenhagen noticed that, well, suppose I can get a good border rank for a direct sum of matrix products, so a bunch of independent ones. And this border rank could be much smaller than the sum of the individual border ranks for all we know. And in fact, we have examples where it is. And then, even if we have a bound on the border rank of a direct sum, we can get a bound on omega, which is given by this interesting quantity, which is just the product of the dimensions of the matrix product to some value tau, which is roughly omega over 3, summed, and that has to be equal to the border rank. So the point of this is that here's an approach to getting bounds on omega. I find some tensor, and it happens to be a direct sum of matrix products. I bound its border rank, and this immediately gives me a bound on omega via this equality here. So, and this was the approach that was taken by Schoenhagen. Later it has been refined, and I'll give you some intuition about the refinement. Okay, so suppose I am working with a tensor that's not a direct sum of matrix product, but maybe it looks like this in the following way. So there's this notion of restriction of a tensor, which basically, if the vector spaces have the same dimensions, then it's like a change of coordinates. But if they're not, it's just a three homomorphisms that take each vector space to the vector space of the other tensor. And it has the property that T prime is a restriction of T if you can obtain it by mapping the individual vector spaces of T into the ones of T prime. And the nice thing is that if T prime is a restriction of T, then its border rank is at most the border rank of T prime. Okay, so then this gives another approach. I take a tensor, I bound its border rank, and I show that a direct sum of matrix products is a restriction of it. And then I immediately get a bound on this. And there have been some papers that do this. Okay, but it turns out that something even better can be done. It's pretty simple, right? Instead of proving that the direct sum of matrix products is a restriction of the tensor, then we just showed that the direct sum is a restriction of a large tensor power of the tensor, and then again we can get a bound on omega from this equality now, because the border rank of a tensor power is at most the power of the border rank. So, and this is in principle, this is exactly the approach that all the papers since Schoenhage actually take. We take a tensor, we blow it up, we know a bound on its border rank, then we search for a direct sum of matrix product in it, and we apply Schoenhage's inequality up there. So this is the approach. And so now I have to tell you about how you find direct sums of matrix product in tensors. So it turns out that restrictions can be difficult to work with. So we don't know actually how to argue about arbitrary restrictions of tensors. So let's just pick special restrictions. So what's a special restriction? Well, it's some sort of zeroing out. So if you look at the trilinear form that corresponds to a tensor, then I say that another tensor can be obtained by zeroing out from this one if I can just set a bunch of these xi, yj, and zk's to 0 and get the new one. So here's an example. Let's say I have this one, x1, y0, z1, x1, y1, z1. Then if I set y0 to 0, I will restrict only to this term. And this type of restriction, it's pretty simple to argue about. It's very combinatorial, and it's much easier to obtain algorithms from it. And again, because it is a special restriction, we again have this easy proposition that if you restrict t prime to t, then the border rank of t is at most the border rank of t prime. And we can apply Schoenhage's theorem using a zeroing out of some tensor whose border rank we do understand. Right, so the whole thing is that we don't have a very good understanding of matrix products and their direct sums, but maybe we have an understanding of some other tensor. And we can gain an understanding of these direct sums of matrix products if we can embed them into the tensor we do understand. Okay, so from now on, I'm just going to talk about zeroing out. So there are special types of restrictions. And the simpler goal is I take something I understand, I take it to the nth power, and now this power is so vast that I can somehow zero more things out and find matrix product within it. And after that, I apply the Schoenhage theorem about it. Okay, and this type of zeroing out also has names they're called combinatorial restrictions or combinatorial degenerations, depending on where you read about them. Okay, so because we're working with n by n matrix multiplications, often it's nice if the tensor we're starting from is symmetric. But sometimes they're not, so let's symmetrize them. What is symmetrization? Let's say I have some permutation that's over 3 elements, and it acts on a tensor by shifting the roles of the x, y, z variables. So what I mean by this, it takes the indices of x and makes them indices of z, and the indices of y makes them indices of x and z, y. So if I have this tensor, then I want to shift 0, 1, 2 into 1, 2, 0. And 1, 0, 1, I want to shift it to 0, 1, 1. So just a shift. And then I can symmetrize the tensor by taking t tensored with pi t tensored with pi squared t. And now all the variables, they have roughly the same indices up to permutation. It all looks very nice. And of course, we have a bound on the border rank of the symmetrized tensor, which is in most the border rank of the original 1 cubed. So now we have the symmetrization trick, and we're going to use it. Okay, so something that was defined by Coppersmith and Winograd in their original paper was something called the value of the tensor. So given a tensor, I want to know how good is it to simulate a matrix multiplication algorithm. And intuitively it says, oh, it's a value, the value function is a non-decreasing function of tau, and I want to think about if I have a border rank bound on the tensor, then how good is this bound into giving me an n to the 3 tau matrix multiplication algorithm. And here's a definition. So for every tensor power of the tensor, the symmetrized tensor n, you look at all the possible zeroing outs into a direct sum of matrix products. And these zeroing outs could have different dimensions, so they depend, the dimensions may depend on the zeroing out sigma, and there can be different numbers of these. But so there's some number of these for each particular tensor power n, and then we define the value of the tensor as the third root of the value of its symmetrized one. And the value of the symmetrized one is you take the limit as n goes to infinity, and then when you look at a particular n, you take the maximum out of the zeroings outs of this value, which comes from the Schoenhagen theorem, to the 1 over nth power. So this is a little bit technical, so some intuition is that, well, we want to find the maximum n such that this value here equals the border rank to the n power, which is our bound on the border rank of the nth power of the tensor. Yes?
Can you repeat what is the symmetrizer? So what is T sign?
Yeah, what is the symmetrized version? This is the symmetrized version. I take x, y, and z, and I shift the rows of the x, y, and z variables.
So it's
You better call it balancing than symmetrizing.
It's balancing.
'Cause it doesn't make it a symmetric tensor.
Well, it
Not a
depends.
symmetric
No, it's just.
No, it's
she's
balancing.
just
Okay,
making
sure.
it balanced.
I want the indices of the x variables, y variables, and the z variables to be roughly the same up to permutation. That's all I want. So it's balanced. Yeah.
So it's a coordinate dependent. It's not a group action. I don't understand.
No, it's not. It's group action on the x, y, and z's.
Instead of a tensor in, say, V1 tensor V2 tensor V3, you're looking at a tensor in
V3,
V1
V2.
plus V2 plus V3 tensor to the third power.
I see.
So it's
Yeah, but it's like shifted though. It's pi t is.
It's just Giorgio's confused because we usually reserve the word symmetrizing for making it into a symmetric tensor.
Okay.
Oh,
But this
okay.
is
Well,
not what's going on.
well, this
Yeah.
is a different symmetrization. Symmetrization prime. Okay.
Symmetrizes the format of the tensor.
Yeah, exactly. Yeah, it's just nicer this way when I'm. This, yeah.
When you start, it's already
No, the
symmetric.
format.
Well, so the border when you permute the rows, the border rank stays the same. So the border rank of t and pi t is the same. And then, so when I tensor product, I get that the border rank is at most the cube. So it's at most the product of the three things, and they're all the same. So that's why.
Is it possible to have strict inequality?
Where?
This one, the border rank of a tensor product of two tensors strictly less than. Why is it inequality?
Well, the right-hand side just tells you if you have an expression for the border rank tensor,
Sure.
then cubing that will give you an expression.
Yeah.
That doesn't tell you that's got to be the best way.
Yeah.
Yeah.
So it can be strict inequality, right?
Could be. We don't know.
So you don't use that you don't use that.
It doesn't matter for my purposes,
Okay, I see.
because I always have less or equal to.
So people used to think the additive analog of this, that you
It's
had
false,
to have equality, and that was shown to be false.
For border
So
rank.
by Schoenhagen, so no one is going to say anything about whether they believe you could have strict inequality or not, because they were bitten before.
Yeah, well, it could be true. We don't know. Yeah. Yes.
So T and pi t, if you tensor them together, what do you mean? Do you just mean you do disjointly, or do you use the same variables again? Because these, as you write them, T and pi t use the same variables. Do you just
Oh no, they don't need. I just by tensoring I mean do different indices.
Okay.
Yeah, that's the usual thing. So they don't use the same variables. I just did this for illustration purposes.
Oh, okay, I see. Okay.
So I mean, you can think of this x prime, y prime, z
Sure,
prime.
sure.
Okay. Good point. Okay. Right, so now I've symmetrized this thing and I want to define this value that we're going to use. And the value is, I take the symmetrized tensor, look at large tensor powers, and I look at what this quantity here looks like to the nth, and the nth root of it as you let n grow. And this limit has been shown to exist, and I'll give you a generalization of Schoenhager's theorem that only uses values. And that's what we use. So one simple lemma you can show is that these value functions, they're always super multiplicative and super additive. So we have direct sum of two tensors, then the value of their direct sum is at least the sum of the values, and the same with the tensor product. And this allows for a relatively simple proof of the following theorem that has been implicitly used since Coppersmith and Winograd, which is if you have some tensor and you can show that its value in terms of tau is at least the border rank of the tensor, then omega is at most 3 tau. So this seems like the right thing to analyze. This value function gives us a way to analyze omega, just like the Schoenhager theorem allowed us to analyze it before. But now this value function is in the limit, whereas the Schoenhager theorem wasn't. And we can gain from this. So now the approach is I obtain some lower bound on the value function, and I have an upper bound on the border rank, and if I combine these together with this theorem, I get a bound on omega. So this is the approach everyone uses since Coppersmith and Winograd. I take some t with known border rank, I guess some value of tau, which such that omega will be less than 3 tau. Then I do some search, which is somewhat complicated, and it searches for these zeroings out in a particular value of n, and then you take the limit as n grows, and then you obtain a lower bound on the value at the particular fixed tau that you picked. Then you check if this value is at least the border rank. If it is, then you try to decrease it, and otherwise you increase it, and you do some binary search. And this thing here is often a somewhat nasty constraint program, which you have to define and you have to solve with actual solvers. So first you have to prove a theorem about what happens as n grows and take the limits, and then you maximize this thing subject to a bunch of constraints. So I'll give you some intuition about how this has been done in the last several papers. So this is the tensor that Coppersmith and Winograd started with. It's actually a family of tensors for integers q from 2 to whatever you want. The actual q that has been used is 5 and 6, and nothing else has been used. And the tensor looks like this. It has 3 terms here that are actually matrix multiplication tensors, and 3 terms here that are also matrix multiplication tensors, but they're just scalar multiplications. And if you would like to look at it in this nice pictorial view that I recently learned, so if you can have a matrix where the x variables are the columns, they index the columns, the y variables index the rows, and the z variables are placed. So in the xi, yj entry, you place the z variable that appears in the tensor. And then for CW, you have zeros here. These 3 entries here correspond to the 3 scalar multiplications. This here, and this here, and this here, they correspond to the matrix products that are at the top. So this is what this tensor looks like, and as Q grows, it becomes longer and longer. So the nice thing that's known is that the border rank of this tensor is exactly Q plus 2, which is the number of x, y, or z variables. And Coppersmith and Winograd analyzed the value of this tensor and the tensor squared. And then they concluded from this second value that omega is at most 2.376. Okay, so this is this. So now I'll give you some ideas about how they approached this and how they analyzed the value of this tensor, and then show you how we improved omega after that. Okay, so they defined something called a blocking. So you're given a tensor and you decide to take the variables and their indices and sort of partition them into blocks. And so you assign every index, let's say of the x or y or z variables, some integer called blocks of I, so that whenever the tensor is non-zero, let's say Tijk is non-zero, the block I plus block j plus block k equals b, and b is a global integer. So stare at it a little bit. It's unclear why they should exist, but it exists for many tensors. So here's an example of the CW tensor. I can place any variable with a 0 index in block 0, a variable with an index q plus 1 in block 2, and all the others in block 1. And then let me just write the block numbers above the variables. And then you will see that for any triple here that corresponds to a place where Tijk is non-zero, I will have that the sums of the blocks is exactly 2. So 1 plus 1 plus 0 is 2, and 0 plus 0 plus 2 is 2. And so this is a blocking of the CW tensor. And you can devise such blockings for many things. Okay, so why do we care? Why do we want to do this? Well, a blocking partitions a tensor into a sum of smaller tensors. And these smaller tensors maybe are easier to understand. So in particular, we look at the subtensor that corresponds to the triples that have the x variables in block I, y variable in block j, and z variable in block k, where k is b minus I minus j, and maybe we can analyze these subtensors much more easily, and then worry about removing shared variables after that. So I'll say a little bit more about this. So here's the example for the Coppersmith-Winograd tensor. I have the blocking as before, and this defines a partitioning of this tensor into these triples. And each of these block triples is a small tensor by itself, and they actually are matrix multiplication tensors. So x1, y1, z0 is actually the sum over I of xi, yi, z0, and this is a 1 by q by q by 1 matrix multiplication. So this blocking gives a partitioning of the tensor of this particular tensor into matrix products, a sum of matrix products, which if it were a direct sum, then we would be done, but it's not, because these things share variables. And the goal later on is just to remove the shared variables and apply the value theorem on this. So here's more. So again, the blocking gives some partitioning of the tensor, and hopefully we know lower bounds on the values of each partition, each particular summand. And if the sum were a direct sum, then we just apply this, and we get that the value of the tensor is at least the sum of the values of the smaller pieces. But if it's not, the idea is to remove the shared variables in a large tensor power. And why do you want to do it in a large tensor power? Because we have more degrees of freedom. And we're doing this zeroing out. We're basically the intuition is when I take the big tensor power, I again have some block triples, and if I set whole blocks of variables to 0, then actually I'll remove some shared variables. And there's a nice framework about how to do this in a principled manner, so that to retain a large fraction of these summands while still having,
So after doing all that, your inequality will suffer, the right-hand side will be diminished.
Yeah, so if you do zeroings out, basically this side, you have fewer summands than you had before, but you hope that you still retained enough to get a bound on omega.
But for this general method, do you know, usually, well, not usually, but just from the formalities from the formalism of the method, do you always know how much you lose?
I'll show you how much you lose, yeah. I won't tell you exactly the details of the method, but I will show you how much you lose if you use a symmetrized tensor and this. Well, I'll show you. Thanks. Okay. So now, we're going to look at T-sim, and we're going to zero out a bunch of blocks, and we want to obtain many summands on the right-hand side. So the way we're going to do that is in a sort of a combinatorial way. So we can actually argue about how much is left. And we're going to first define fractions. So for every block I, every block j and every block k of the x, y, z variables, I'm going to pick some fractions, xi, y, j, and zk. They're fractions, so they always sum to 1. What's their purpose? What's the purpose is, well, if you look at the nth tensor power of a tensor, the variable indices are just n-length sequences of the original indices, and you can also find, you can get a blocking in the same way by giving blocks that are n-length sequences of the original blocks. So this is a well-defined blocking, and then this blocking gives a partitioning of the nth tensor power into many more block triples. And so now what we're going to do is actually we're going to zero out all the x variables in the nth tensor power that don't have exactly x sub I times n indices of block y, y sub j indices of block n, of blocks j, and zk times n indices of block k for variable z. So when I do this, I know exactly how many block triples remain, and it also allows me to argue about the value of these triples. So let me tell you more about this. So if once I have picked these variables x, y, and z, I know exactly how many variable blocks remain at t sim to the nth power, because I do the same thing to t to the nth power, pi t to the nth power, and pi squared t to the nth. So now I have a handle on how many variable blocks remain, and my goal is to get that all of the summands have the same value. If I can do that, then I can I can argue about how many things remain once I zero out. Okay, so let's argue a little bit. So suppose that after I've zeroed out a bunch of these blocks, what remains is that all of so t to the n is a sum of block triples, and after I zero out a bunch of blocks, suppose I have exactly aij times n indices in which every one of these triples looks like x sub I, y sub j, z sub k from the original tensor. Suppose I do that, then I know that every one of these summands that remain has value, at least the value of this xi, yj, zk to the aijk times n power, the product over ij. So I've picked some fractions for which I look like xi, yj, and zk. I zero out everything that doesn't look like this, and what remains is a sum of these small tensors whose value I understand. And what's the relationship of aijk, of these fractions of the triples, to the fractions of the blocks that I zeroed out? It's actually a linear system. So the sum over k of aijk is exactly x sub I. The same holds for yj, but the sum over I, and the same holds for zk. So I have a linear relationship between the blocks that I pick to zero out and the triples that remain, and these fractions of triples define the values of the summands that I have remain. Okay, so the point here is, well, if this linear system here has full rank, then just picking what to zero out in the blocks will give me exactly the values of the summands, because there's only one choice for the aijk's. And we get a sum of tensors all of the same value. And this is exactly what happens in Coppersmith and Winograd. So I wrote that up again, and this is the theorem that Coppersmith and Winograd actually prove if you go through what they're doing. So they prove that in the special case when that linear system has full rank, and if the underlying tensor is symmetric in the sense that I said, which is the case of the Coppersmith-Winograd tensor, then the value of the tensor for any, as n goes, is larger, is at least this red piece here to the 1 over 3nth power times this value that I told you is the value of each summand divided by a polynomial in n to the 1 over n. And then what you do is you take n going to infinity, take Stirling's approximation, and you get that the value of the tensor is this quantity here. And it's completely dependent on the choice of xi, yj, zk, and they're constrained by the fact that there's some for each I, xi is equals to 1, yj equals to, the sum over yj is 1, the sum of zk is 1, and the aijk's are completely determined from the xi, yj, zk when you solve the linear system. So this is the theorem that Coppersmith and Winograd prove, and they prove it for this particular case of the CW tensor, but you can continue and do it for all tensors that are symmetric and have this property of the blocking. And a little bit of where does this come from, and let me tell you where does that come from. Well, the number of summands up here, so it's a sum of tensors each of value this much. The number of summands is the number of x blocks in tsim to the nth power once I zero things out, times the number of block triples that contain an x block. And this first portion is exactly this red part over here, because this is the multinomial coefficient that chooses xi times n positions out of n that have to remain non-zero, and same here and same here. So this is what the red part is, and there's some portion here that is lost by the analysis, which is the number of triples containing an x block. So what the analysis of Coppersmith and Winograd does is it takes the original number of sums and the number of triples that actually remain after they're zeroing out is only the red part. The blue part is the loss that you suffer. So, okay. So the point of their theorem is that there is a nice bound you can get of the value of a particular tensor from a constraint program, and you just plug it in, and because solve the constraint program. And I did this for the same when your linear system defined by the blocking doesn't have full rank, and then your theorem looks like this. The value of the tensor is at least what we had before from the Coppersmith and Winograd theorem times some ratio over here, which is very bizarre. And what's bizarre is this is the g of aijk is the loss we incurred by zeroing out. This is the fraction of triples that disappeared. And so you get this ratio over here. But in order to compute this ratio, you have to solve this thing. So you have these constraints up here. The top two are the ones we had before. They're linear constraints in the linear system. But the last one is basically BIJK has to maximize the loss that we're incurring, subject to it being also a solution of the same linear system. So basically, the point is we get the same type of constraint with a little bit of change that comes from the fact that the linear system no longer has full rank. And it allows us to analyze much larger tensors and a larger number of blocks than we had before. So again, you can take Stirling and then goes to infinity and you get this bound. So now you have a simple recipe of computing the value of a tensor and trying to extract bounds on omega from it, which is you form this constraint program, you're maximizing this nasty thing, and you just, and it works. So let me give you a quick example of how you do it. So here's this simple tensor. The tensor looks like this. It has two copies of the same tensor. Maybe this is transposed. Okay, A, and then and some tensor B over here. And the two A's may share variables, but B does not share variables with A. Okay, and now I can get this blocking. It's a natural blocking. I put all the first X variables here in block 0, the second into block 1, 0 and 1. And then the variables of A get mapped to block 0 and there.
A's are two identical tensors, right? So the two A's are two identical tensors.
They don't have to be identical. They just have to have the same value, and they can share variables. But yeah. So you can this can be like A and A can be different tensors, but they have the same value as far as we know. And then B is some different one, and B does not share variables with A. So any tensor that looks like this, you can analyze in the following way. You block the variables 0, 1, 0, 1, and then the variables of B get block 1, and the variables of A get block 0. Then we proceed to pick fractions, okay? The 0 variables here and here get a fraction of A, because it's kind of symmetric, and the x1 and y1 get fractions 1 minus A. Then you get a fraction of B for the variables of A, and fraction of 1 minus B for the variables of B. Okay? And then you say, well, the fractions of the block triples is for block triple 1, 0, 0, and 0, 1, 0, which is exactly where the A's are. So 1, 0, and 0 is where A is, for example. You give a fraction of x, and for whenever it has to look like B, you get a fraction of 1 minus 2x. Then you notice this is the linear system. It says that A has to be equal to the pink stuff, 1 minus 2x plus x, and also B has to equal 2x. Okay, so you have a linear system, and you see, oh, it has full rank. So because it has full rank, well, this means that Aijk equals Bijk in my formulation up there in the red. So this portion there disappears. This ratio doesn't matter anymore. And then you just plug in. You plug in your x0, y0, and x1, y1, and so on. You take them to the appropriate powers over here to the 1/3. This should be over 3 here.
So I'm a little confused. So this tensor is a tensor B plus a tensor A plus a tensor like A prime that has the same value as A. And then
And the two A's share variables, but B doesn't with A.
so B is completely disjoint, or B shares like the Z variables with the A's? I'm a little confused.
So B shares these x variables with that A, and these y variables with that A, but it doesn't share any Z variables.
I see.
Yeah. So this is the structure, and then you perform the blocking, you get that it's a valid blocking, and then you do these fractions, you get the linear system from the fact that when I pick this fraction, the fraction of B and A that are in here has to sum to the same thing. So it's A is 1 minus 2x plus x, You can get the same for the fraction of a is b is equals 2x, because there's 2 copies of a. And then you see that this thing has full rank, and then you just apply the formula. You get that the value is this, and actually I forgot the 1/3 fraction here, which comes from symmetrization. So for any tensor, you can get some blocking, and you can get this thing. The value that you get may or may not be close to the real value, so you're getting just a lower bound on the value. But sometimes it's good enough to get omega, some bound on omega. Okay. One extra interesting thing is that if your original tensor is small, then it may only allow for only one blocking, for example. So you're very constrained in what you're analyzing. So for example, this tensor in the matrix form, it only allows one blocking, because if you put these two x variables in the same block, then you're forced to put the y variables in the same block, because z0 appears in both cases. So there's this small tensor only allows for one interesting blocking, so one blocking. But if you go to a tensor power of this thing, you can get more blockings, things that don't look like tensor powers of the original one. So something like this, let's say the second tensor power of this thing looks like this. And the induced blocking from the original one is just to take the block sequences of the original things. But instead, I could just merge these two blocks and these two blocks, and all of a sudden I have a completely new blocking with fewer blocks and more things in it. And it turns out you can get better bounds on the value from the second tensor power of this than from the first. And this goes on. The higher the tensor power, the more diverse blockings you get, and the more interesting it gets, and the better the bound on the value you can get. So it's an interesting combinatorial question to analyze what happens in general, but we don't really understand it even for the special case of Coppersmith and Winograd. Okay, and then the point is, instead of taking t as your starting tensor, you can take t to the k for some k, and you can improve. So for example, Coppersmith and Winograd analyzed the second tensor power, and they showed it gives 2.376, but the first only gets 2.388. So the same things happened later. So Stoddard showed that if you look at the fourth tensor power, then you get 2.374. So this 6 becomes a 4 with a new blocking. And then you can get a different blocking for the 8th tensor power, and you get a little bit better. And Legel, he showed the 16 and 32nd power makes this 8 into a 7, and so on. So you can continue this fashion. And the whole thing comes from the fact that you're analyzing completely new ways to partition your tensor, and the analysis gives you something better. All right, so this is a type of blocking that has been used, and nothing else really has been used. So, okay, this is pretty much the last slide. One more after this. So the induced blocking. So when you take a blocking and you take the second tensor power, you just do indices of blocking the sequences. And what has been used is, well, I take the sums. For each index sequence, I take the sum of the blocks in it, and this defines a new blocking. For example, 0 plus 0 is 0, 1 plus 1, and 2 plus 0, and 0 plus 2 is 2. So you're actually merging original blocks. And this new type of blocking is the only thing that has been analyzed. So you take the kth tensor power of the Coppersmith-Winograd tensor, look at the induced blocking, merge the blocks using this summing operation, and you get a new blocking, and you analyze this. It turns out you can analyze this recursively. You can get bounds on the values. So this is the only types of blocks that have been analyzed, sums of blocks, and sometimes linear combination of blocks. And again, the warning is that once you merge blocks, you get tensors you may not understand, so you have to do the value lower bounding technique on them separately. But the same framework works, which is nice. And one slide on computational issues. So here's the program. that I had, so up to here is very nice. So it's a concave program if you look at it. But once you add this constraints, it behaves really nastily. So it took some work to get it to be solved. So it makes it difficult to solve. The fact that you have to do some extra maximization in it, it becomes nasty. But later on, Francois is going to talk about how he slightly loosened the constraint and made it easier to solve for higher tensor powers. In a summary, we have a simple recipe to get lower bounds on the value of any tensor. You find some blocking, you form and solve a constraint program which is given by the theorem, and you get something. Hopefully, for some new tensor, you'll get a better bound on omega. Okay, and one limitation is that apparently, so I am told that if you restrict yourself to do blockings obtained via merging, then you cannot get a better bound on omega if you start from the Coppersmith-Winograd tensor or its tensor powers. So if you want to get two, either use different blockings or use a more general restriction or a different tensor. So don't use zeroing out or use some other tensor. So you have to change the framework maybe. But there is some limitation on this approach. And that's it.
Further questions?
So in the previous slide you had 3 escapes, and here you seem to propose that tensors is the way to go. Tensors is the way to go.
Tensors will be the easiest one because I just apply the framework. For the others, I have to think about what happens if I don't do zeroing out. I have to change my framework. Or like if I use a different blocking, I have to understand how to get these blockings when I'm not doing simple algebraic manipulations of the original ones. So yeah, that's why. That's the simplest. But it could be the others are doable too.
So it's very important from your tensor at the beginning that border rank was smaller with respect to rank.
That would be interesting to understand. What is the relationship between the value and the rank? I don't actually know what it is. But it seems like there's some relationship because we're trying to find something of high value, low border rank. If the value has something to do with the rank, then we're looking for tensors that have a big gap between border rank and rank. But we still don't understand.
In your this formulation, this sigma aij, do you have any restriction on the zeros? Let's say some aijk must be 0 or not?
Let me see which one. So basically, you mean
this is relation. We already have this. You see xi. You want xi and yi, yj, and zk to equals 1, right?
yes.
And then it's in the last thing. And do you restrict that? Let's say some aijk must be 0 or not?
The sum of aij.
Not some of them. Let's say a111. You want them to 0. Is there constraint like that?
No, I don't have a constraint like that. Why do you ask?
Because some people studied this problem of this non-negative sums. It's sort of like it's triple stochastic, and you assume that you want some entries aijk to be equal 0, so you cannot always have it, and so there are some conditions.
So we don't have that, but we have this annoying other condition about the bijk. So this thing. So we have these extra variables so it's a constraint program within the constraint program that I have to solve. And so that's the thing. All the other constraints are linear. I don't care if what you set the AJKs to, as long as they're a bit bigger than 0 and sum to 1.
Okay, well, thank you again, and we come back at 11:40 actually.